Welcome and good day to you all. Today we are going to do and complete basically the bubble cap tray design part. This we have continued from the previous lecture and we moved like this. In the last lecture what we have done is we have found out the diameter of the bubble cap tray or plate, whatever you may call, by two methods. One was Southwards-Brown method, the other one was Fair and Matthews. We have decided the tray spacing. We have been aware of the bubble cap details. We have also gone through the tables which contain these details, and we have found out that what our tray layout should be. At the same time, we have talked about the different sections of the tray and how they are to be introduced inside the column itself. Any tray will have some amount of entrainment, and this is going to reduce the Murphy tray efficiency of that specific tray, and how to estimate the revised Murphy tray efficiency, that also we have seen. That means, we know at this particular point of time the diameter, definitely the tray spacing, which leads to the total height of the column, definitely the details and the layout of the bubble cap on the tray itself in the active area, and the revised efficiency we have recalculated. In order to have a complete delivery of the design of the tray, we are also to supply, or rather we are also to find out the liquid gradient across the tray. We know very well, and we just recapitulate that a liquid gradient across the tray should be as low as possible to ensure that you have a proper cross flow. If you have a large gradient of liquid over a tray, in that case wherever you have lower liquid, your flow is going to be more, and here definitely it will be less. Obviously, here will be less flow of vapor, because the resistance to flow will be much more. We definitely have to have an idea about the pressure drop between these two. That means, what is the delta P across the tray? And we will try to find out a systematic way of estimating the same, because we definitely will be having a pressure difference between the column bottom and the top, but we have to ensure that this pressure difference is not large, because it makes a difference in the volatility at the top and the bottom of the tray. While designing the sieve tray with downcomer, the details of how to find out the backup in the downcomer and how exactly it affects the performance of a tray, that has been told to you. So, we are not going to repeat it. There is another aspect of any tray which is very important. A tray normally will be having a vapor flow up approaching it, a liquid flow down which is approaching it. The vapor will be leaving and the liquid will be coming down ultimately. That means, you will definitely be having the liquid flow, but it is not across the tray directly. That means, it goes like this and then falls. So, I will just show the liquid flow this way. It comes through the downcomer, but it is also possible and it is necessary at times to have holes. The holes should be on the tray, it's on the, I will just show you where it is. In case of a sieve tray, there were many holes. So, quite naturally what we wanted that it should flow across and it should not leak. That means, this type of flow is called the weep of the tray. That means, during normal operation I do not want any weeping, but During operation, I have a level of liquid. Once my operation of the column stops, what I do not want any liquid to remain up. So, what I want is basically all the liquid in my tray, all the liquid in my trays should gradually drain down and get accumulated from where I can take it out. That means, I want this type of weeping to take place only when my column is not in operation. During operation, I do not want my trays to weep. Now, in case of a sieve tray, you already have holes. It does not weep because you have a vapor here which is approaching these holes, and definitely there is a pressure gradient P plus delta here, P plus delta P, and here you have a lower pressure which is only P. So, that also holds the liquid, it does not allow weeping through the tray itself. This is to some extent is also true in case of your valve trays. In your valve trays, what you have? In your valve trays, you have you have a hole, you have typically a plate with legs. Now, what is normally done is the edges of the plate that you have, they are upturned only at certain points. So, when it rests like this. So, what happens is there is possibility of the weeping which can take place this way. So, it weeps. So, you do not require provision of weep holes in case of your valve trays, and obviously you do not need in case of sieve plates. You do not need this. In case of the other type, which is the bubble cap, you definitely will be needing it. Let us go for the simplest thing to tackle. We will tackle the weep hole and its provision first. The purpose of a weep hole is gradual drainage. That means, when my operation stops, from the tray, I want everything to come, all the liquid to get collected in the column bottom. And why it happens, we just explained that. Now, this draining will be necessary where it will be needed on all blocked portion of the deck. That means, where it does not drain naturally or freely. What are these places and locations? Suppose this is a bubble cap tray. I am not showing the bubble cap here. This is the downcomer of the upper tray, and this is the downcomer belonging to this tray. So, what you have here, you will have your bubble caps, and you have a downcomer backup. The liquid flows this way. This portion of the tray, particularly of any type, I mean, if it is a sieve tray with a downcomer, even on the sieve tray or in any other places, you will require this portion to be drained. So, in case you want, you may be required to provide the weep holes in this part in case of valve trays. So, in valve trays, you will be having the weep holes only here. But in case of bubble cap, you have to have it here, you have to have it here, you have to have it here, because you want your entire tray to be drained. So, the same thing is true in case of seal pans. If you have a downcomer seal pan, if you have a downcomer which is like this, and you have a seal pan which is like this, you must have a set of weep holes here which will allow draining of this when the column is not in operation. We definitely do not want any weeping to happen perceptibly during operation. Typical weep hole sizes are 3 to 5 millimeter, which could be punched in most of the cases and drilled in some very rare case. typical number of typical area provided for weeping per tray, per meter square of tray is 275 to 280 millimeter square per meter square. You note the unit here, it is millimeter square per meter square of net open liquid area. Now, the question is, why net open liquid area? Net open liquid area means wherever you have a liquid level. So, this includes for your tray the downcomer area also, and it is to be summed up over all trays. So, anywhere you have a liquid level and its surface area has to be summed up in meter square, and you provide 275 to 280 millimeter square of weeping area per meter square of the area that you have just now determined. Now, why do we need to have these weeping arrangement? We want that after my operation has stopped, possibly I will be sending my column for maintenance. Typical time we allow for a column to cool down is roughly about 4 to 6 hours. So, there is an empirical expression which talks about estimating the draining time of the tower in minutes, which is this theta. Theta is in minutes. N is the actual number of trays which is provided in your tower. The liquid drains through the weep holes, so naturally its viscosity is important. If its viscosity goes up, draining time should go up. So, naturally it will be involving VOL as well. Now, heavier the liquid, more will be the static head allowing it to pass through the weep hole. So, quite naturally theta is inversely related to rho L, and rho L appears at the denominator. Now, what you provide? You provide a weep hole area. The weep hole area here in this case is denoted by a particular dimension d equivalent of weep hole. That means, it is basically the area of a circle having the same area as all the weep holes put together. So, you can have its definition here. It is a diameter of a circle whose area is same as the total area of weep holes on one tray. That is the formal definition. Now, there is one more interesting thing, that how much of liquid to be drained. The how much of liquid to be drained is depending on how much of liquid was present. So, when you have a tray which is not in an operation, you have an outlet wear which is here. So, naturally you are expected to have, if there is no draining, this will be your liquid level. It is also possible that when you have a bubble cap, you have which has got a riser over the deck, and it goes like this. The riser height here maybe is HR. When nothing is there, there is no air, there is no gas flow this way. So, the liquid is expected to come and get drained automatically up to this. So, after draining, the draining would start normally at the actual tray level. So, the actual tray level is expected to be the lower of these two. That means, if my HR is higher, then I will be saying that HR is the level. If HW is higher, sorry, the other one is the level. So, what we have here is the lower of the bubble cap riser height and the height of the overflow wear. I believe there is only one more item, which is ANL, which is a net open liquid area of one tray. So, that basically gives us an idea that how much of liquid has to be drained from that particular tray. This is how you estimate. Now, my question is, how do we use it? Typical time for draining is 6 to 8 hours. So, we know theta. If you have defined your system, that everything here except this term is known. So, if I set my theta to be either 6 or 8 hours, mind it that your theta has to be in minutes, and in that case we can find out the D equivalent, and we know the total area of all holes on one tray. Now, what do? We decide whether we are going to have 3 millimeter, 4 millimeter or 5 millimeter holes. Typically, it is either 3 or 5. On bigger trays you have 5, on smaller trays you have 3, and there is one more thing which is also there. It also depends on the viscosity of the material that is being handled, and also the surface tension, because there is depending on the surface tension, the liquid, whether it will pass through naturally through a hole or not, that is decided. So, you usually will be using 3 or 5, and based on that you fix up the number of holes. So, your number of hole is basically determined once you have decided the weep hole diameter to be, say, maybe 5 millimeter. In that case you find the number of weep holes. So, this is how you find the weep holes, and in fact, this is the simplest part of it. The next part of it is basically, if my tray has to operate smoothly and without any channeling of the vapor going through the thinner layer of liquid, we must have as low a difference in the level of liquid over the tray. Here we have a schematic of the tray again once more. Here is my deck, this is my deck, and the caps are not shown here. We have also exaggerated the level difference. What you will find here is something very interesting. You will definitely have a outlet wear with a height HW, and when it flows over this, you require a minimum of 6 to 10 millimeters of liquid level above this, which is basically HOW. So, while designing, you must have considered HOW anything between 6 and 10. If it is below 6, normally the passage of liquid over the wear is non-uniform. So, that you have to avoid. Now, what you have to do is basically you have a look at the bubble caps. The bubble cap which is mounted here offers resistance to the liquid flow. Let us see what all things affect this resistance. One is, I have the riser here and I have my clearance below the cap, which is basically clearance below the shroud, which is small s, and this is also small s. If we can have, or rather we will have a specific gap between the caps. Also the caps will have a diameter b. So, quite naturally, if I have this A small, my resistance will be more. If I have B large, it is going to affect my resistance of flow to my liquid. So, these are basically the points which is going to decide what exactly is going to be the pressure drop of the liquid in flowing from this point to this point. So, the basic equation here what you have is QL is the flow of liquid, LW is the length of the wear, CD is a coefficient of, it is something very much similar to the coefficient of discharge, it is basically a frictional coefficient, is related to this particular geometry, which is defined by the term gamma is equal to A upon B. So, here you have a gamma term. Delta is what? Delta is basically the difference of level. See, if you have your caps oriented this way and if you have your flow of liquid this way, the head difference between these consecutive rows is basically small delta. Quite naturally, if this is per row and if you have n number of rows, n rows, then your total difference is going to be this delta multiplied by the number of rows. So, that we are going to use later on, but the way delta is related to the other parameters is given here. So, this is delta and here you have a delta. So, you find that this is not an explicit expression in delta, but it has got delta in the implicit form. Now what you have? You have basically S, you have gamma, and you have HLO. We will see this in the next slide. Now what you have here is basically what is HLO? It is height of liquid over the wear. So all these are here. There is another way to express or find out the same term in using another expression, which uses a parameter small f. The small f is basically related to the frictional drop. QL is the flow rate of liquid across the tray, and you have a mean tray width. For example, if you have a tray which looks like this, it has got the upper tray downcomer, the downcomer which is blanked, and this tray downcomer is here. The path length is here. The width of the path starts from here, goes to a maximum value and ends here. So what you take basically is an approximate average, which is the midway of these. It's basically a trapezoid which is taken, and you take this particular gap as the mean tray width. Now this mean tray width at the denominator and the numerator, if you have QL, you know the value of small f. So once you know the value of small f, it's possible for you to evaluate this, and you know this value. So this point, at this point of time, I will say this is a known value. While you are designing, you definitely know your QL. You already have gone for your layout of the tray. So you are very much aware of the numerical value of the mean tray width as well. Now this delta refers to no vapor flow rate. This refers to no vapor flow rate. So if I solve this particular expression by trial, I will be getting a difference between the level on this and this when there is no vapor flow rate. So we got to correct it for the vapor flow rate now. The total delta, as I have already said, is delta multiplied by the number of rows perpendicular to the liquid flow direction, which is small n, that I have already said. You have to have a correction for this now, which is CV. CV is read from a graph. The graph is here. CV here, let us have a look. This graph is typically in the x axis is in GPM, which is the liquid load per foot mean tray width. That means if you have a tray width of LW in foot, the flow rate of liquid in gallons per minute, US gallons per minute, in fact, this is US GPM. In that case, you will be knowing what exactly is going to be your liquid load per foot mean tray width. So sorry, I made a mistake because I possibly had said LW. It's not the LW, but basically it's a mean train width that has to be used here. So we know the x coordinate now. There is a parameter in this particular graph which is V0 into root V. The V0 into root V is basically, I have redrawn the same thing here. The V0 into root V is what? The V0 is root V is basically the volumetric flow rate multiplied by rho V, and I have already converted the constant so that you have this particular parameter in the unit of your whatever is the parameter here, which is basically in FPS units. So once I know my V0 root V, possibly if it is 0.85 or something like this, I will have a curve like this. If I have my x axis, I will be taking this and I will be coming here, and possibly I will be reading my CV value to be 0.92. So this is how you generate the delta P corrected for the vapor flow. You will notice one thing here, it involves both the vapor flow rate as well as the liquid load. And remember, this is a technique, this technique is valid only for bubble cap trays, this particular correlation. The third part that we are going to deal with is basically the tray pressure drop, which is H tray, which is going to be expressed finally in the millimeters of the liquid which is there on the tray itself. If we look at the tray and the tray pressure drop, we will find that if my tray is dry, there is no liquid on it and I am passing the same amount of vapor through it, there will be a particular pressure drop. Quite naturally, if this pressure drop itself is high, when my performing tray I am talking about, that will also be high. So, it is said that it is a sum total of 3 components, the dry tray pressure drop, which we will estimate somehow using certain other things. Then what we add? We add the pressure drop in my aerated liquid. My bubble cap is surrounded by what? My bubble cap is surrounded by liquid. In fact, it is aerated liquid. So, what I have to add here is basically the pressure drop due to the aerated liquid, which is present on the tray itself. Now, what else is left? What I have said about is about the dry pressure drop. That means, if I have my cap like this and my riser ends here, I will also have here slots. I will have my slots here, which are the openings. Now, what happens is, whenever there is a flow of vapor, the vapor has to come out through the slots, and while doing it, it has to displace the upper portion of it with vapor, and this portion of it will be the liquid and the upper portion will be the vapor, which will come out and form bubbles. Now, what we do is, in order to remove the liquid from its front, there will be an additional component of pressure drop, which is basically the strop, which is basically the seal, the slot opening pressure drop. So, the total pressure drop on a tray is found out by sum total of all these. The dry pressure drop is basically found out from an empirical expression, which is related to naturally the riser area and the riser velocity. So, the riser velocity is the vapor flow rate divided by the total riser area, and it is related to rho v into this divided by rho L, because we would like to convert the total pressure drop in terms of the liquid. Now, this Kc is an empirical term which is found out from a correlation which relates to the annulus area to the riser area. What is the annulus area? If I look at my bubble cap, I have my riser at the central. So, this is going to be my annulus area and my riser area is this part. The ratio of this two typically should be between 1 and 1.5, and this is what is used in evaluating the Kc value, which is used in the estimating the dry tray pressure drop. Next, what we do is basically the same thing. We have to estimate now the percentage of the slot opening, because the pressure drop which is encountered at the slot outlet as the vapor comes out will depend on how much opening it is present there. This is found out again with a graph. The geometry of the slot is definitely very important. The slot can have rectangular section, the shape, or it could also have a tapered geometry. So, all these three are combined in a very interesting way. If this is given called H and this is called W, when my W by H is 0, which is nothing but my RS, this is basically what? It is a triangular slot. When RS is 0.5, typically it is a trapezoidal slot, because in conventionally the trapezoidal slot that are used, they have their width half their base length. You can have anything in between also, and you can interpolate, but that's the most standard trapezoidal slot which is used. You could also have a rectangular slot when your W becomes equal to the base length, and so this is a curve for that. Depending on these, you have a factor defined. The factor is here. While estimating QV max, that means when the entire slot is open, because there is a large amount of vapor which is trying to come out, in that case you will have naturally the maximum vapor flow rate. Empirically, it will be related to the area of the slot, which is my AS. It will also be related to the pressure drop across the slot itself, and it will also be depending on the vapor and the liquid densities. So this gives us the maximum vapor velocity that can happen. AS is the number of slot area per tray in meter square, and QV max is in meter cube per second, HS is in millimeter, and rho is in kg per meter cube. Now, what I do here is basically I stop at this particular point, because with this it is possible for you to estimate the maximum vapor velocity, and based on this you have to first check whether your vapor slots are overloaded. If they are overloaded, this is the way you evaluate your slot pressure drop, for which the slots which are, if they are not fully loaded, basically what you find, you are basically QV divided by QV max. If it is less than 1, it is not fully loaded, that means you have a partial opening of your slot. So basically what it is happening here is basically the slot opening assuming clear liquid. So you find out what is going to be a pressure drop in this particular case. For loaded slot, it is the head loss is equivalent to the slot opening. It is as if you have a level of liquid here. This is the level of liquid which you had. It is being pushed here and it gets removed, and this is the additional pressure drop that you have. In case of overloaded slots, it can always happen that your slots are fully open and you are still pushing more. That means this in this case is greater than 1, that means it is a overloaded. In that case, what you do is you add the height of the shroud ring, because what happens is in case of overloaded slot, the shroud ring is immediately below, this portion is your shroud ring. So naturally you will have your bubbles coming out from below the shroud ring as well, and so that gets added. So this is how you estimate, you find out the different components of the H tray, which is the dry tray pressure drop, the slot opening pressure drop, and the aerated liquid pressure drop in case of bubble caps. With this, I think if you are supposed to design a bubble cap tray, your steps will be finding out the diameter, finding out the tray spacing, finding out the total height of your column, finding out the slope or the gradient of liquid on your tray. Before that, definitely you have to find out what exactly will be your layout, and you have to go into the details of your layout. And beyond that, what you will do is you will find out your the tray pressure drop exactly the way we have discussed. I think with this we will complete our topic here today, and after this we will start the design of packed columns. Thank you all.